Okay. Good morning, everyone. Yeah, so basically, okay, for today's lesson, okay, we will actually look into what we call as Bronsted-Lowry's theory of acid and bases. Yeah. So if you look at this acid and bases, okay, so we should know, okay, that acid, okay, can be divided, okay, into what we call as strong acid and as well as weak acid. So what are strong acids? Okay, strong acid is going to be acid that dissociates completely, yeah, or almost completely in a solution. It means in a solution means it requires water, yeah, so aqueous solution. So in a solution, okay, to give you, okay, the ions, yeah, and then they are going to be called strong acid. And most of the time, okay, if you look at this acid, like for example mineral acids, hydrochloric acid, sulfuric acid, nitric acid, all the common acids that you know, they are all strong acids. So you need to know that if I write HCl, okay, you need to know that they dissociate completely, one single arrow, H plus and Cl minus. Okay, we are still under Equilibria, yeah, so later we will go into and look into reversible reaction. But for this one, okay, there is no reversible reaction. So HCl to give you H plus and Cl minus. H2SO4 also, okay, later I'll show you one example, but generally they are going to give you this, okay, 2H plus, okay, and so on. Okay, so please take note of that. Okay, and then, okay, do remember, okay, we can also write this particular equation, okay, with the reaction with water, because instead of just simply writing it like that, okay, you can also include with water. So HCl, when you react with water, okay, they are going to give you, okay, H3O plus Cl minus. Is still the same, yeah. So this is what we call as hydroxonium ion, yeah, hydroxonium ion, which is any acid will contain hydroxonium ion, okay, which is this H plus will join with the H2O to give you hydroxonium ion. That will give you the property of the acid, yeah. So that is going to be how we write the equation, okay. But when we look at weak acid, okay, in your syllabus, the weak acid that they want you to know is going to be CH3COOH, which is your ethanoic acid. Okay, but here they have given most of the organic acid like HCN, hydrogen sulfide, okay, and then carbonic acid. Okay, all this they are going to say that they are weak acid. But I am going to show based on the syllabus. Okay, if this one ethanoic acid, you must have a reversible sign. And you are going to have CH3COO minus plus H plus, okay. So if I use, okay, in terms of water, so I need to write CH3COOH plus H2O, doesn't change, still reversible equation. You are going to get CH3COO minus, the H plus will join with H2O to give you H3O plus, which is called as hydroxonium, yeah, ion. So this hydroxonium ion is the one that is going to be responsible in giving the acidic property for the acid, yeah, please take note. So in this case, what is important over here, when to use, okay, this and when to use this, yeah. So we use, okay, for strong acid completely dissociate, we use a single arrow. If you have a weak acid, okay, then we are going to use a reversible arrow, yeah, quite simple, yeah. Now the common acids, okay, of course, okay, it's stated in your syllabus, so I will go through the common acid and the common alkali. The common acid is going to be hydrochloric acid, HCl. So you need to know, okay, when I write the equation, I will use H2O in everything now, okay, because I think straight away dissociation I think you can do easily, yeah. So this one is going to be H3O plus to give you Cl minus, yeah. And then sulfuric acid, so H2SO4, okay, if I react with H2O, okay, they are going to give you, okay, H3O plus, okay, SO4 2 minus, okay, so there is 2, so this one is going to be 2, okay, this one, okay, I think better not to write, yeah, it's going to be more complicated. I'll just write the common one first for the H2SO4. Okay, but later I will explain a little bit more on H2SO4. H2SO4, I'm just going to write 2H plus SO4 2 minus. Okay, for nitric acid, okay, so I can still write, I think this one easier. Okay, if I write down, it's going to give you H3O plus NO3 minus. Okay, but for ethanoic acid, okay, CH3COOH plus water, do remember it's a weak acid, yeah, so this one, all these are strong acid, this one is weak acid. How do I know which one is strong acid, which one is weak acid? You memorize, like what I told you, yeah, you memorize the ethanoic acid, memorize now. Okay, it's a weak acid. Okay, so organic acids are going to be weak acid, mineral acids are going to be strong acid. What is mineral acid? Yeah, mineral acid is anything that do not have carbon and hydrogen. Organic acid has, okay, carbon and hydrogen. Yeah, so here, okay, they are going to have a reversible sign, okay, and you will have CH3COO minus ethanoic ion plus H3O plus, the hydroxonium ion. Okay, quite simple, yeah. So if you move on, okay, this is why I told you just now, I will actually go through the sulfuric acid again. So just to check again whether you guys are listening. So Mayumi, is sulfuric acid a strong acid, Mayumi?
Yes.
Yes, yeah, correct, yeah. So sulfuric acid is a strong acid. Do remember the only one that I want you to know for now, yeah. For now, the weak acid is going to be ethanoic acid. Okay, the rest of them, okay, the common ones, sulfuric acid, nitric acid, yeah, hydrochloric acid, all these are strong acid. But okay, please remember one special thing about this strong acid, yeah, about sulfuric acid. So acid, this is outside of the syllabus. Acid can be divided into monoprotic acid. Monoprotic acid means the acid contains only one H plus, so HCl, monoprotic acid. We also have diprotic acid, where the acid can actually have two H plus, for example H2SO4. Okay, we also have triprotic acid, where the acid can actually have three H plus. Okay, so can someone, okay, Kathleen, can you give me one example of triprotic acid that you know?
Oh, CH3COO.
No?
CH.
Even though the ethanoic acid, yeah, ethanoic acid still give you the one H plus only, yeah. So it's still considered to be monoprotic. Triprotic involving P, H3P what?
PO4.
Yes, phosphoric acid. Good, yeah, good, Rico. So H3PO4, okay, is going to be one example of triprotic acid, yeah. So do remember, for monoprotic acid, no problem, yeah. Monoprotic acid, HCl, okay, they will give you HCl, they give you H plus and Cl minus just directly. But for diprotic and triprotic, they are going to release the H plus one by one. Yeah, so please remember that. So if you have H2SO4, okay, what happens actually? H2SO4, in the beginning, they will give you H plus, one H plus, yeah. Then they give you HSO4 minus, negative and plus to give you 0, yeah. So here, okay, they are going to give you this first, and this is strong, yeah. But the second, okay, HSO4 minus, when they give you another H plus, do remember it's not a straight, a single arrow. Now this is going to be a reversible reaction. So they give you H plus SO4 2 minus. You see, plus and 2 minus, they will give you minus over there. Okay, so this is going to be something that you need to remember. Okay, the first equation is going to be straight, okay, just a single reaction, but okay, HSO4 minus, okay, can still, yeah, form an equilibrium, yeah, to give you H plus and SO4 2 minus. So now, okay, but overall, okay, overall, okay, it's still going to be considered to be a strong acid because H2SO4, when you add this and this will cancel, so they are going to be written as this. Okay, I just want you to know. Now, I want you guys, okay, to think what will happen to this H3PO4. Okay, I give you 1 minute. Okay, you try to write the same equation like this, 1 and 2, but for this, okay, they will have 3 equations. Okay, 1 minute. Okay, those who are writing, yeah, you continue to write, yeah, but those who are not writing or don't have any idea, you just listen to me, yeah. So now, okay, for this, what is going to happen? Okay, H3PO4, they will give you 1 H plus and H2PO4 minus. Okay, plus and minus will give you 0, so you will get 0 here. And then what happens next? You take this one, yeah. So H2PO4 minus, they are going to have a reversible. Okay, so you have another H plus given out to give you HPO4 2 minus. 2 minus and plus will give you minus. Okay. And then the last one, HPO4 2 minus, they will give you the final H plus to give you PO4 3 minus. Okay, and finally, okay, when we add all of them, okay, we are going to get, okay, H3PO4 to give you 3H plus plus PO4 3 minus. Okay, now my question today is go and find out. Okay, this one you go and find out whether is H3PO4 is considered to be a strong acid or weak acid. Okay, this is your homework. Yeah, go and find out. Okay, phosphoric acid is going to be considered a strong acid or weak acid. Yeah, so that is going to be homework for today. Yeah, so now, okay, let's move on. Okay, so when we move on over here, okay, we are going to look into base. Yeah, so of course earlier we looked into this acid. We have strong acid and weak acid. So now we are going to look into this strong base and weak base. Now for strong base, okay, if you look at this strong base, okay, strong base is defined over here. They are going to dissociate completely or almost completely in a solution. Okay, and then bases that dissociate to only a small extent, yeah, in a solution, they are called weak base. So let's look at what is a strong base. Most of the group 1 metal hydroxides are strong bases. Example, KOH, NaOH. Okay, all these are group 1 metal hydroxide. They are strong bases. Yeah, when they dissolve, okay, they are going to give you K plus and OH minus. Okay, Na plus and OH minus. Okay, but bases that dissociate to a small extent. Okay, example, there are many here. Okay, but in your syllabus they want only ammonia, so I'll just focus on ammonia. Yeah, ammonia. Okay, in order to show for ammonia, because you see, if you have KOH, I can say K plus ion plus OH minus ion. But in this case, you cannot just simply break the ammonia. Yeah, so in this case, you must show with water. Yeah, you must show with water. Okay, because ammonia, okay, they dissolve in water. Yeah, and if you because it's a weak base, they must be a reversible reaction. And okay, what happens over here is the H2O, okay, they will give the H plus to to ammonia to give you NH4 plus ammonium ion left with OH minus. Okay, so this is going to be how, okay, the ammonia, the weak base, okay, how they are going to form the bases, or alkaline solution. Okay, so here according to syllabus, okay, the common alkalis are going to be sodium hydroxide, potassium hydroxide, which is going to be considered to be a strong base. But ammonia, okay, I told you, is going to be considered as weak base. Okay, but from here, okay, you will notice one thing. Why Mr. Gopi used base? Why Mr. Gopi suddenly used alkali? Okay, what is alkali? What is base then? So it is important to know that. Okay, so in that case now, okay, we are in checkpoint number 2. What is base? What is alkali? Okay, so let's actually check now. So what do you think is a base, Anderson? What is acid, a base? What is alkali? What's the difference between them, Anderson? Not sure, just say not sure. We will move to someone else. Okay, we will move here. Rakesha, what is base and alkali?
Base are proton acceptors and they form hydroxide ions. Alkali is the same as base, but it's soluble in water.
Okay. There are certain things which are correct. Certain things that maybe need to refine a bit. So good. If you have your Venn diagram, so your like your maths. Okay, generally if this one is base, okay, alkali can be subset, subset, okay, which is going to be alkali is base, all alkali are base, okay, but not all bases are alkali, So what is the difference over here? Alkali is actually base that are soluble in water. Okay, which is similar what Rakesha mentioned, soluble in water. Generally, all sodium hydroxide, potassium hydroxide are soluble in water. Okay, so they are going to be alkali. Okay, they are going to be alkali. Even ammonia, okay, being a weak base, they are soluble in water. Okay, they are still going to be considered to be alkali. So ammonia is also alkali. So don't remember that alkali must have only OH minus. No. So alkali is a base that is soluble in water. So what is base generally? Base is going to be any compound, okay, that is hydroxide. Maybe it can be KOH, any OH. And it can be also sodium oxide. It can be also, okay, magnesium oxide. Do remember group 1 and group 2, they are known as alkaline oxide, okay, alkaline metals, so when they react with water, they are going to give you alkaline solution, so all this, okay, they are considered to be oxide or hydroxide, okay, when they react, okay, when they react with acid, they will give you salt and water. So it means what is base? Base is, okay, base is going to be whenever there is going to be a reaction with acid, okay, they'll give you salt and water, okay, which is, you should know what type of reaction is that, okay, which is going to be, can undergo neutralization reaction. It is going to be considered to be a base. So anything that can actually react with water to give you salt and water, or anything that can actually undergo neutralization, okay, they are going to be considered as base. But the base that is soluble in water, okay, they are called alkali. So that is going to be something that you need to remember. So okay, so the answer for this, okay, what is base? Is a compound that contains oxide or hydroxide ion, react with acid to form salt and water. Okay, that's going to be a base. Okay, and then what is alkali? Bases that are soluble in water. They are going to be alkali. Okay, they are not a lot of alkali, a lot of bases, but alkali only few. Okay, sodium hydroxide, ammonia. So you can memorize all this. Now, so let's move on to our lesson today. The lesson, the title today itself, they are called Bronsted-Lowry's acid and base. So previously, whatever that I introduced to you, it's just kind of introduction only. It's just kind of introduction only. But if you look over here, okay, what is happening? Generally, if you have acid and base, okay, there are different ways, okay, of showing acid and base. Okay, like for example, I might say HCl is an acid, okay, because HCl contains H plus. Okay, they can give you H plus, so I say it's an acid. I can say sodium hydroxide is a base because they will give you OH minus. Okay, that is going to be one type of definition. Something that gives you H plus and OH minus is going to be acid and base and so on. Okay, they are but not all the cases. Okay, we can actually use this definition. Okay, therefore there are different theories that came about. One of the theories is Bronsted-Lowry's theory. Okay, there is Lewis acid theory as well. Okay, but we are not going to study about that. We are going to look into Bronsted-Lowry's theory in our syllabus. So according to this syllabus, this theory, okay, do remember this theory. This theory, okay, if you just follow whatever you think about acid, acid must be giving you H plus, base must give you OH minus. Maybe you will find it a bit funny. Why? Water, okay, can be considered as acid and alkali. Okay, do remember, according to this theory, water, okay, although they are neutral, according to this theory, water can be a Bronsted-Lowry acid, Bronsted-Lowry base. Okay, so that doesn't mean they are acid and base like what you think. Acid, you think that acid must have pH less than 7. Okay, base must be pH more than 7. Acid must taste sour. Acid must be corrosive. Oh, water doesn't have all that. Why we can classify them as acid and base? No. This is according to the theory. According to the theory, we are going to look at the definition of the theory. They are going to act as Bronsted-Lowry acid. Act as Bronsted-Lowry's base. Doesn't mean that they are acid. So please remember, they might be different, with what you think. Okay, so according to the theory, Bronsted-Lowry acid is a proton donor. Anything that can donate proton, okay, we consider them as Bronsted-Lowry's acid. Okay, and then Bronsted-Lowry base is going to be a proton acceptor. Okay, so anything, okay, that can accept proton, okay, we can actually put it as, okay, Bronsted-Lowry's base. Now let's actually have a look at this hydrogen. Now if you look at hydrogen, okay, hydrogen is 1 1. Okay, and then the number of proton, okay, is 1. Electron must be the same, so 1. Neutron is going to be 0. Okay, but if I have H plus, okay, 1 1, number of proton is going to be 1. Okay, electron is the one that you remove over here, so it's 0. Neutron still remains 0. So, okay, you can see H plus hydrogen ions, okay, we can consider it, okay, as a proton. Okay, we can consider it as a proton. Now, my question over here is all H plus ions are proton? Russell?
Oh, yes.
Okay, maybe, maybe if we are referring to hydrogen 1. Yeah, so Russell is correct. Yeah, but I think maybe Russell is also forgetting. Maybe this one we learn also. Yeah, maybe Russell also forget. Okay, that we have isotopes. Okay, H11. We also have H21. Okay, we also have H31. Yeah, so let's actually analyze this. Yeah, do remember. Does it actually in this case Russell is correct? Yeah, so let's look at it first. Yeah, how about isotopes? How about isotopes? Isotopes, if you look over here, isotope, in this case of course H plus for this is going to be correct. How about H21? H21 PEN. Proton is 1, electron is 1, neutron is 1. And then if it is going to be H21 plus, proton is 1, electron is 0, but neutron still 1. Are they considered to be still a proton? The answer is no. So Russell's answer may be not 100% correct. So do remember, not all H plus ions are protons. We are talking about this and this. Yeah, of course if you do the 3H1 also it's the same. Yeah, so 3,1H plus, proton is 1, electron is 0, and is still 2. Yeah, so it's not going to be a proton. Yeah, just take note of that. Yeah, so what is important over here is, in this case I'm talking about H plus 1,1. So a proton, is going to be hydrogen 1 ion. Yeah, hydrogen 1 ion. So in this case, let's actually have a look at H2O is changing into H3O plus. What is actually happening? They are receiving the H plus from HCl. Yeah, Nicholas, you can go to toilet. Now they are receiving the H plus from HCl, making HCl is a proton donor and making water as a proton acceptor. So Alden, can you tell me which one is acid, which one is base according to this definition? HCl, is it acid or base, Alden? Not sure, just say not sure, we will move on. Maybe not here, yeah? Or not 100% here during our lesson. I'll move on. So Kyra, can you tell me HCl?
If it's acid or base?
Yes.
HCl, acid.
Yeah, because it's a proton donor, yeah? So this is acid. Water, is a proton acceptor, it's going to be base. So do remember, it doesn't mean water is actually a base, it's a Bronsted-Lowry base. Yeah, Bronsted-Lowry base. So let's actually look at over here, ammonia, then NH4 plus. It means that H plus is given by the water, and they are going to form ammonium ion. So in this case, water is the proton donor. This is a proton acceptor. So let's actually see. Jessica, can you tell me ammonia, is it going to be base or acid?
Base.
Yeah, proton acceptor, this is base. Proton donor, is going to be acid. So do remember, this is, I'm not just telling that water is actually an acid. Water will behave as a Bronsted-Lowry acid because they are donating proton. Now do remember, this is what we call as forward reaction. Okay, we do have, okay, the reverse reaction. Okay, the reverse reaction is going to be this one. Okay, if you follow the reverse reaction, okay, what happens? Okay, ammonia changing to ammonium ion changing into ammonia, they are donating the proton to OH minus. Okay, so this is going to be a proton donor. This is a proton acceptor. So they are going to become acid. This is going to become base. But it's going to be quite difficult, you know, why this one base, acid, this one acid, base is quite confusing. So of course they need to come with a name. Yeah, so of course this one is going to be JC2 stuff. Yeah, I'm not going to elaborate further. Okay, if this one is base and acid, so this one we call it as conjugate. So it's the name that we give, conjugate acid. Okay, and this one is called conjugate base. Okay, this one we will explore further, okay, when we do this in JC2. Yeah, so conjugate acid, conjugate base. Yeah, but anyway, let's actually move on. Yeah, so the checkpoint 3 now. Okay, I will just try B. Okay, maybe I try A over here. So I'm just planning to circle which one is the acid. Yeah, okay, so only acid I'm going to circle. So if you see here, okay, from here, okay, and from here, okay, we know that, okay, there is H plus coming from here. Okay, so I want to circle which one is acid. Okay, this is a proton donor. I circle the proton donor for the forward reaction. Yeah, so let's actually look at the second question. They say right hand side of, identify the right hand side. Yeah, so the conjugate. Yeah, so let's actually look at the right hand side. Okay, you see here, okay, and then suddenly they lose the H plus. Okay, so it means that they are losing the H plus. Okay, they are donating H plus. So this is a proton donor. So I want to look at the proton donor. So this one is the acid or the conjugate acid actually. Okay, so please take note, okay, how to identify, okay, which one is acid or base. Yeah, so I'll just write down, okay, according to Bronsted-Lowry's theory. Okay, so Bronsted-Lowry's theory tell acid and base. Acid is a proton donor, base is going to be a proton acceptor. Okay, so just like that. Yeah, so this one just remember. Yeah, so the next thing is, I think, quite simple. Yeah, so which is, you should know that pH. Yeah, pH, water, pure water will be pH 7. Acid solutions, okay, the pH is going to be below 7. Alkaline solutions, the pH is above 7. And you can see some of the, like vinegar, yeah, vinegar pH 3. Okay, so it's considered to be weak acid. Okay, and then if you look at coffee pH is around 5, so it's a weak acid also. Yeah, and then, okay, that's why I think if you look over here, if you have stomach upset, yeah, or you don't eat anything, you straight away drink coffee, okay, your stomach will have acid, and then coffee is also acidic. Okay, you will have more stomach problem. Yeah, if you drink coffee, okay, with not eating anything. Yeah, so that's going to be one of it. Yeah, and if you look at this, okay, milk of magnesia. Okay, milk of magnesia, whenever you have, okay, acid reflux, okay, in your stomach. Yeah, so of course, okay, we use milk of magnesia so that it neutralizes it. Yeah, so milk of magnesia is going to be pH above 7. Yeah, so let's move on. Okay, so of course, in your syllabus they want you to explain qualitatively behavior between strong acid and weak acid, okay, with reactive metal. So do remember, yeah, acid plus with any metal, okay, they will give you salt plus hydrogen gas. Okay, so this hydrogen gas, okay, they can give you the pop sound, okay, when it is tested with lighted wooden spring. Okay, so this is something that you need to remember. Okay, so if you look at this hydrochloric acid, we know hydrochloric acid is a strong acid. So if I have magnesium ribbon, I just react with HCl, I am going to get magnesium chloride plus hydrogen gas. So of course you can just balance it by putting like this. Okay, so what do you observe? You will see a steady stream of hydrogen bubbles or effervescence being observed. Yeah, and if you use the acid, which is HCl, because HCl gives you H plus and Cl minus, there is a lot of free moving ions over here which can conduct electricity. I told you, in order to conduct electricity, you need either free moving electrons, delocalized electron, or you need free moving ions. So in this case, you have a lot of free moving ions. Of course, if you dip with conductivity electrode, you will get a very good electrical conductivity. And if you dip universal indicator, okay, into this HCl, the indicator will show from maybe from here to here, and it is going to be kind of a darker red color. Yeah, so these are certain things you need to notice. But if I change that and I use a weak acid, and I told you, yeah, the weak acid that I'm going to use, okay, is going to be this, okay, and then magnesium. Yeah, do remember, okay, you do not need to use a reversible reaction for this. Okay, that is reversible reaction. Do remember the title of this lesson: acid base equilibria. Acid base equilibria is going to be reaction between acid and base. So if you are reacting, okay, this and metal, you do not need to show, oh, this is weak acid, I'm going to actually show reversible reaction. No, yeah, this is not going to apply, okay, because equilibria is only for acid and base. Yeah, so therefore this is going to be just like that. Yeah, so you are going to get CH3COO, okay, and then again this is going to be 2 then Mg plus H2. Some of you will be wondering, sir, normally only the positive ions will be in front. Yeah, why like this? If you feel like that, it's okay. Yeah, we normally write like that, but if you still want to write the traditional way, of course, no problem. You just write down like this, plus magnesium to give you MgCH3COO2 plus hydrogen. Yeah, so of course you need 2 there, okay, you need to have 2 there. Yeah, so it's balanced. Okay, so do remember that. But in this case, okay, what do you notice? Now do remember the H plus that is given, okay, is going to be, even though there is going to be hydrogen gas, but the amount of hydrogen bubbles is going to be very, very little. Okay, why? Because, okay, the H plus that is given, okay, to the magnesium is going to be very, very less. Okay, so we are going to actually have a few hydrogen bubbles. If I dip the conductivity electrode, because I have CH3COOH, okay, I am going to give you only few of this. Okay, so it shows a poor electrical conductivity. Why? Only few H plus, only few, okay, CH3COO minus ions are there. Okay, so there is lack of free moving ions. Okay, so because of that, they cannot conduct electricity well. And when you dip it in universal indicator paper, okay, it will show around here, okay, which is going to be more towards, okay, lighter red or orange. Yeah, so let's this one, okay, is I have already mentioned to you earlier. Okay, what is base? Base is any compound that contains hydroxide ion or oxide ion which can react with acid to give you salt and water. Okay, so in this case, okay, that's going to be neutralization can happen. Yeah, so in this case, okay, if you have high sulfuric acid, if I have HCl, I want to react, okay, with sodium hydroxide. Quite simple. they will give you sodium sulfate, salt, and water. Okay, so you just need to put 2 there. Okay, and then you need to put 2 here. Yeah, so done. And then if you have barium hydroxide, okay, barium hydroxide, they will give you barium chloride, okay, plus water. Okay, so if you want to balance, you just put 2 there. Okay, and then there is going to be, okay, 2 here. Okay, then balance. Okay, so do remember, yeah, it will give you salt and water. Now, how do I write the ionic equation? I will take this, copy here, and then I put it here. If you want to write ionic equation for any neutralization reaction, yeah, I'll just use this example first to show. We have already learned about ionic equation. Okay, whenever you have these ions, you see this one aqueous, dissolve in water. Sodium salts all dissolve in water. Yeah, water will not simply change, because water, even though they can change into H plus and OH minus, okay, if it is like this, we just keep it as H2O. Most of it contain, okay, it's going to be in form of H2O. Yeah, so if I want to separate them into ions, okay, I have 2H plus, I have SO4 2 minus, I have 2Na plus, I have 2OH minus, 2Na plus, SO4 2 minus, plus 2H2O. Okay, and let's actually look at what we can cancel. Yeah, in this case, this one and this one I can cancel. And then I can also cancel this and this. Now I just want to know the ions that I cancel, Rebecca. So these ions that I cancel, Rebecca, what are they called as? Not sure?
Not sure.
Yeah, not sure. Yeah, just say pass. Yeah. So anyway, yeah. So let's actually ask someone else. Audrey. No response. Chloe?
Spectator ions.
Okay, good. Okay, spectator ion. Okay, so the spectator ions are ions that do not actually take part in the reaction. So when I remove that, I have 2H plus and 2OH minus to give you 2H2O. You can cancel the 2. I have H plus plus OH minus to give you H2O. So this one, finally I just put aqueous, and this is liquid. This is going to be the ionic equation of all neutralization reaction. Yeah, so please take note of that. Okay, so now, okay, what I want to teach you is going to be this indicator, okay, and acid-base titration. But before I move on, okay, any questions up to here? Just to check, we have lesson until 9:45 or 9:15?
9:45.
Okay, we still have time. Yeah. So let's actually summarize first. Yeah. So Haruto, can you summarize what we have learned until now?
We learned about the base and what how to
Why don't you model?
Okay, Haruto, I'll help you, yeah, a little bit, yeah, so you can just see, you can just explain while I just move, yeah. Okay. Or maybe Nicholas, okay, can you summarize what you have learned?
There's 2 types of acids. There's strong and weak acids, and then there's 2 types of bases also, strong and weak.
I taught you about what is base, what is alkali, yeah. Okay. Okay. What else you learned?
From Stolt-Lowry theory, where acid is the proton donor and then the base is the proton acceptor.
Okay. I think this one is okay lah. Okay, neutralization also I've done, then ionic equation. So overall, yeah, whatever that we have learned, okay, is not actually a big stuff. Yeah, it's not, even though it looks a bit difficult and so on, it's not really very important. Yeah, it's just still at the tip of the iceberg. It's just we didn't really explore further. Yeah, what we explored over here is just a very basic, because it helps us to understand, okay, about what we are going to do now, which is going to be, it helps us to understand about this, okay, because, okay, for this, okay, what happens is going to be, we are going to learn about indicator and acid-base titration. Yeah, because again, the title of today's lesson is going to be acid-base equilibria. Of course, not it shouldn't be titled as acid and base. Yeah, that is not what we want to learn. Okay, it's still acid-base equilibria. There are big portion of this, okay, we will learn in JC2. Yeah, but the one that we are going to learn, this one, according to this new syllabus, they have bring this, okay, in from JC2, they have brought it back to JC1. So whatever that you are learning now, okay, after this is going to be a component that used to be learned in JC2. Okay, so we this is called the pH graph. Yeah, pH graph. But okay, I want you to have a look at this first. Yeah, so this one, okay, is phenolphthalein. Yeah, phenolphthalein, the structure of phenolphthalein. Do you need to memorize this structure? The answer is definitely no. Yeah, you don't need to memorize any of this structure over here. Yeah, so what is this? Okay, this is basically to tell us that when you use indicator, okay, indicator will also follow equilibrium. Yeah, so the indicator, okay, when they are going to be colorless, this is the structure of the indicator, and when they are pink, okay, phenolphthalein, when they are pink, this is the structure. And in simple way, okay, let's actually look at it in this way. Yeah, here there is hydrogen, there is no hydrogen. So maybe, okay, what I do is I just put this simplifier, H indicator. Okay, H indicator. They are going to be at equilibrium with H plus ion with indicator ion, which is, this is indicator ion, the minus ion. Okay, so let's actually bring this up a bit so that we don't get confused so much. Okay, we just bring it up, make it bigger. Okay, now what we do over here is, okay, when I use this phenolphthalein, yeah, so phenolphthalein, okay, when I have H plus, when I have OH minus, I just want to check whether you guys know what is the phenolphthalein color change. Yeah, recall phenolphthalein, when they are going to be acid, what is the color? Acid. When they are base or higher pH, lower pH.
If it's base, it's pink.
Okay, if it is base, it's pink. Good, right on track. So if it is going to be pH which is low, colorless. Yeah. So okay, now you see. Yeah, let's actually come back to that later. Yeah. So now, if I have H plus. Okay, if I have H plus, and I have told you also about this. Okay, I told you that if you have H plus, okay, this is going to increase the concentration of this equilibrium, the H plus over there. So now, Mayumi, can you tell me what will happen to the position of the equilibrium now? According to Le Chatelier's principle, you need to decrease the H plus. How do you decrease the H plus?
The equilibrium shift to the left.
Yeah, you have to use it up. Yeah, you have to use it up. So it means that, okay, you are going to move towards this left, which is going to be the colorless. And have a look over here. When pH is low, it's colorless. So this one will be formed more. Yeah. So that's going to be happening over there. So let's actually look at what happens if you have OH minus now. I erase this one first. What happens with OH minus? Now, if I use OH minus, there's no OH minus in the equation. Okay. So what the OH minus will do, they will react with this H plus. OH minus react with H plus to give you H2O. So when they react, what happens to the concentration? Drop. Okay, so when the concentration of H plus drops, okay, what will happen? Okay, what will happen? So Kalista, can you tell me what will happen to the position of the equilibrium?
It will shift to the right.
Yeah, it will shift to the right. So when they are shifted to the right, okay, wait, yeah. When they are shifted to the right, yeah. When they are shifted to the right, okay, what happens? Basically, you are forming something that is going to be pink in color. Yeah, pink in color. So you can see when I have pH which is high, which is going to give you the pink. Yeah. So basically, just want you to appreciate about this indicator. Okay, they work based on the principle of equilibrium and Link-Chatterley's principle. Yeah. So basically, they will form more. Yeah. Just now when OH, yeah, they will form more of this. That will give you the pink color. Yeah. So here, okay, please read. I have explained whatever which is in this slide over there. Okay, but okay, now okay, what I want to go is the table. Yeah. Now this table is given in your textbook. Okay, but okay, a lot of students. The next question that students will ask: do we need to memorize it? Yeah. If you follow the syllabus, okay, no. Yeah. Select suitable indicators given appropriate data. Yeah, so in paper 1 and paper 2, maybe if they ask, they might give you the might only. Yeah, I'm not going to be 100% certain. Yeah, pH range should be given. Yeah, because given appropriate data. But okay, I want you to remember about paper 3. Now, paper 3, with all the practical that we have done, even, okay, they give you the qualitative analysis notes. They never give you that, oh, the endpoint for methyl orange is going to be this color. The endpoint for phenolphthalein is going to be changing from pink to become colorless or colorless to change into pink. No, they never say that. So, you still need to memorize the color changes. Yeah. pH range, maybe you no need to memorize, but color changes you must memorize. But it's going to be crazy if I want to memorize everything. Yeah, therefore, I will select 4 main indicators that you might want to consider to memorize. Yeah, okay, memorize means you still memorize the pH range as well. Yeah, the popular ones will be phenolphthalein, of course. Yeah, phenolphthalein, okay, you can see 8.2 to 10. Okay. And we are going to memorize bromothymol blue, okay, quite popular as well. Okay, methyl orange is very popular as well. Okay, and then another one that is going to be very popular is methyl red. So there are 4 that I have indicated over here, which can be very popular. Yeah, popular only. Yeah, whether you want to memorize or not, it's up to you. Yeah. But I have already mentioned, given appropriate data, but for paper 3, it will not be given. Yeah, please take note of that. Okay, but now, okay, let's actually look at this graph, okay, drawing graph, because this is going to be under syllabus 9. Yeah, so sketch the pH titration curve of titration using combinations of strong and weak acid. Okay, and then we need to select suitable indicator. Yeah. So here, okay, if you have, okay, previously whatever information that we learned, okay, it just comes down to this. Yeah, if let's say I have sodium hydroxide and ACl, yeah, and then sodium hydroxide we know is a strong base, ACl is strong acid. So I'm just going to say strong base with strong acid. Okay, strong base and strong acid. There's few information that you need to follow. Yeah, like for example, the graph starts at 13. Okay, ends at somewhere 1. Okay, why 13? Because it's a strong base, so 13. Okay, ACl is a strong acid, so ends at 1. Yeah, and okay, what is important? Another thing is, if let's say for example, if you have a burette, okay, and then I have the conical flask, and normally I put the indicator in the conical flask and I put a pH meter inside. Yeah, so my question is, there will be solutions in burette, there will be solution in your conical flask. I just want to know which one, okay, will be sodium hydroxide. Is it going to be in the burette or is it going to be in the conical flask based on the graph? Okay, so in this case, let's actually try to ask, who should we ask? Let me check first. Let's ask Adrian.
Can you repeat?
Okay, the question is, sodium hydroxide will be in burette or is it going to be in conical flask based on this graph? This is the pH meter, yeah? pH meter is the one that going to measure the pH. So, sodium hydroxide is in burette or conical flask?
In the conical flask.
Yes, okay, because it start at 13. Yeah, start at 13. The pH meter is there. So of course the sodium hydroxide. Okay, so it is measuring sodium hydroxide in the beginning. Yeah, and as you put on the ACl, okay, the pH will drop. Yeah, pH is dropping. So anyway, yeah, that is actually the basic over there. So what else that I want you to observe over here is the numbers. Yeah. The numbers that I want you to observe over here is going to be when is the sharp drop. Yeah, when is the sharp drop, okay, or the sharp fall. Okay, the sharp fall is going to be between 10.5, okay, to 3.5. Okay, so you can see around 10.5 sharp fall to 3.5 around here. Okay, there is a sharp fall over here, and okay, that is what we call as midpoint of the steep slope. Yeah, midpoint of this is the midpoint, which is going to be 7. Yeah, so this is going to be, okay, 7, and then okay, this is 20. This one is what we call as the equivalence point. Later I will explain to you the difference between equivalence point or end point. Okay, so pH 7. So there's few numbers that I want you to memorize. What are those numbers? Okay, 13, 1, 7, the midpoint, 10.5, 3.5. Then these numbers, once you know, you can actually apply, or you can sketch the graph. Okay, now it's already a bit messy. We just go to the next slide. Okay, still same graph. Yeah, if you look at this 10.5 all the way to 3.5, this is a sharp drop, and they have used bromothymol blue. Let's actually go back here. Bromothymol blue, the pH range is 6 to 7.6. okay, let's actually 6 to 7.6, and I use, let's say, the red highlight over here. 6 is here, 7.6 here, within here. And if I bring this highlight and I bring it closer to here, it comes within the sharp fall, which is the sharp fall is from here to here. If there is going to be, okay, if you have the indicator pH range is within the sharp fall, not necessarily must be within at 7, yeah. Within the sharp fall, it is suitable to be used, and it can give you color change that we can observe the endpoint, which is the bromothymol blue is blue to change to yellow because it's dropping sharply. So it means that there will be immediate color change from blue to become yellow. So it's a very good indicator to be used. Okay, what happens if I use phenolphthalein? Yeah, phenolphthalein, the pH range, if you look up, okay, is going to be from 8.2 to 10. So if I bring it closer, they are still within the sharp drop, yeah. Even though they are not at here, which is the pH 7, the midpoint, doesn't matter, yeah, as long as they within the 10.5 to 3.5, within the sharp fall, they are suitable. They can give you, the pink color will change into colorless. They can give you. So it's not necessarily must be within the 7, yeah, within that 3.5 to 10.5. So something that you want to memorize, yeah. Now that's for strong acid and strong base. Okay, let's actually move on. If you use strong acid and weak base, what are the examples? Strong acid, you see, nitric acid is a strong acid. Ammonia is a weak base. What are the changes that you will notice? Yeah, let's actually look at nitric acid pH is going to be 1. Yeah, because strong acid. But ammonia, previously sodium hydroxide I used pH 13, yeah, but now it's not going to be 13. Now we are going to use 11, you see. Because it's a weak base. They start at 11. They end at 1. Okay, they start at 11, end at 1. Okay, previously the drop is 10.5 to 3.5, but now it's not going to be 10.5. The drop is going to be from 7.5 to 3.5. So you can see from 7.5 to 3.5, somewhere here. Okay, and the midpoint of the sharp fall is no longer at 7 like previously. If you look at this midpoint, midpoints are supposed to be here. The midpoint is going to be 5. Okay, the midpoint is 5. So these are the numbers that I want you to remember. 3.5, 7.5, midpoint is 5. Okay, so using this, okay, let's actually see which one is a suitable indicator. Okay, methyl rate. Okay, let's look at methyl rate. Methyl rate is going to be 4.2 to 6.3. Okay, let's actually put 4.2 to 6.3 here. 4.2 maybe somewhere here, 6.3 somewhere here, so from here to here. So let's actually bring it there, 4.2, 6.3. So 4.2, 6.3 somewhere here. Okay, and you can see that they come within the sharp fall. Yeah. They are, so we can use methyl rate. Okay, they will give you a proper color change. Yeah, but if you use phenolphthalein, okay, phenolphthalein, yeah, so now let's say I use a different color, green. Phenolphthalein is 8.2 to 10. 8.2 to 10. They will come under here. Okay, so Jessica, do you think is it going to be suitable for using it as an indicator for this? Are you there, Jessica? Okay, I cannot hear anything, so maybe I'll just ask someone else. Patricia?
Can you repeat the question, sir?
Okay. Do you think the one that I highlighted green over here, which is going to be phenolphthalein range here, 8.2 okay, to 10, do you think is suitable to be used as an indicator for this?
No.
No, because they are not within the sharp fall range. Yeah, so you cannot use phenolphthalein. Yeah, so that's actually the explanation for this. Okay, do remember the numbers that I want you to memorize here. 11, 1, 5, this 7.5, 3.5, okay, That's all. Yeah, those are the numbers that I want you to memorize. So let's move on. Okay, weak acid, strong base. Okay, weak acid, strong base. Now, weak acid, strong base, example you see here, sodium hydroxide. Normally, weak acid we deal with ethanoic acid. Now they are using benzoic acid. So do remember, benzoic acid is a weak acid. Yeah. So sodium hydroxide is a strong base. pH must be starting from 13. Benzoic acid is a weak acid, so pH will be up to 4, not 1 anymore. So you see 13 up to 4. Okay. And then, okay, normally, okay, strong acid, strong base 3.5, 10.5 to 3.5. So just now, okay, if you are using strong acid, okay, weak base, then it's going to be 7.5 to 3.5. But now, it should be from 10.5 to 7.5. So from 10.5 to 7.5, somewhere here. This is going to be the sharp fall. Okay, sharp fall. And okay, when you have this sharp fall, do remember the midpoint of the sharp fall is somewhere here, which is 9. Yeah, if you follow closely, okay, previously the midpoint is going to be from 7. If you are using strong base weak acid, you follow base will be at 9. You see, like what we do. And then if you are using strong acid, okay, and weak base, the pH will be 5. Okay, so like what we did just now. So maybe something that can actually help you to memorize. Yeah, so this is going to be the midpoint for strong base and weak acid. This is strong acid, strong base. This is strong acid, weak base. Okay. And then the numbers, okay, I told you what are the numbers that you need to memorize and so on. But anyways, let's see what you use. Okay, phenolphthalein instead of methyl orange. Why phenolphthalein? Let's look at phenolphthalein. 8.2 to 10, so somewhere here. Okay, so suitable. Okay, within the sharp fall. But if you use methyl orange, okay, let's look at the methyl orange. Methyl orange is going to be from 3.2 to 4.4. Okay, let's see. 3.2 to 4.4, so somewhere here. Cannot. Okay, you cannot use methyl orange because they do not, okay, have the pH range which falls within the sharp fall of the graph. Okay, so you cannot use methyl orange. Okay, that's the explanation. Now, do remember the numbers here. Number, and the number. Yeah. And then if you look at the last one, okay, which is the weak acid and weak base. Now, weak acid and weak base, there is no sharp fall. Yeah, there is no sharp fall. Okay, I think this one also, I think there is some error over here. I'll show you first. Okay, so here, aqueous ammonia is a weak base, so better weak base we use 11. Okay, not 13. Yeah. And we will use, okay, weak acid is going to be 4. So from 11 to 4. So here they use more than 12. I will use 11. Yeah. Okay, so what I will do, okay, I will erase this part, okay, just to make it, okay, easier for us. Okay, we will start from 11. From here to here, they will decrease. Okay, they will decrease. And then, okay, they will end at 4. Okay, and then you can see there is no sharp fall over here. No sharp fall. Okay, but, okay, the middle, yeah, the midpoint is still 7. Okay, they are still 7. Okay, but because there is no sharp fall, okay, even though they are still bromothymol blue, okay, it's going to be still can be seen, yeah, but it's not so accurate, it's not so useful, okay, to use, because whenever we use indicator, we want something to change immediately. If you use bromothymol blue, maybe within the range. Okay, bromothymol blue is going to be, the color change is from yellow to blue. You see, from yellow to blue, if they take time, they don't change suddenly. They take time. Yellow, maybe change into slowly into green, then slowly into blue. We won't know when to stop. Okay, we won't know when to stop. Okay, therefore, it's not going to be a very good suitable indicator, even though, okay, the best is bromothymol blue. Yeah. So there is no sharp fall. Yeah, there is no sharp fall, because when we want to use indicator, we want to see an exact color change, maybe from pink to become colorless, okay, from certain color to become certain color. In this case, if they are changing gradually, it's going to be difficult for us to identify. Okay, so I will go through two questions over here. Yeah, so they say suggest a suitable indicator to find the endpoint of nitric acid and ammonia. Nitric acid is a strong acid, ammonia is a weak base. So nitric acid, okay, the pH will be 1, ammonia, the pH is going to be 11. Okay, so if I draw the graph 1 to 11, yeah, so 11 first, okay, so 11 to 1, okay, the graph maybe somewhere here, okay. So the sharp fall, okay, I told you to remember, if it is going to be strong acid, weak base. If it is strong acid, strong base, 10.5 to 3.5. Strong acid, weak base, okay, it is going to be 7.5 to 3.5. You follow a little bit to strong acid a bit, yeah, you bring it down. If you have strong base, weak acid, then it's going to be 10.5 to 7.5. So in this case, we are dealing with strong acid, weak base, okay, so 7.5 to 3.5. So maybe this one is 7.5, this one 3.5, okay, so I will drop all the way here, then continue like this. Okay, so that's my graph roughly. Yeah, and then we want to know, okay, okay, which one is going to be the suitable indicator. Okay, let's say we want anything from 3.5 to 7.5. So let's see, 3.5 to 7.5, which one I can use? I cannot use this. Okay, 3.5 maybe can, 3.5 to maybe can, 3.5 maybe can, 3.5 to 7.5 can. This one 3.5 to 7 can. Okay, cannot. Okay, but in this case, let's select the popular one. Yeah, I told you the popular one, metal red. Okay, don't select the one not so popular. Yeah, so maybe I can choose either these two. Yeah, but I will choose metal red. Yeah, metal red. Okay, so let's check the answer. Okay, so you see the answer will be metal red. Okay, an explanation is there. The steepest part, okay, is going to be 7.5 to 3.5. The indicator is range within this region will be suitable. Yeah. So here, okay, another question here. Suggest why phenolphthalein cannot be used, okay, to find the endpoint of hydrochloric acid and urea. HCl is a strong acid, urea is a weak base. Okay, so I told you strong acid, weak base, strong acid, weak base is here. Okay, so 7.5 to 3.5. I think it's the same graph, yeah. Okay, same graph as the first one. So they are asking why phenolphthalein cannot be used. Phenolphthalein, you see 8.2 to 10, yeah, you can check 8.2 to 10. So if I put 8.2 to 10 somewhere here, okay, somewhere there, okay, let's see, somewhere here. So it doesn't lie, okay, at the range that we want. So you see what is the answer. Okay, phenolphthalein, okay, do not have the correspond to the steepest part of the pH volume curve. So you can just check, yeah. So later, okay, I will give you this PowerPoint, yeah. I'm planning to put in the breakout room, but later I noticed that you cannot watch YouTube because MDM is still going to be active. No point to put you there. But you will get the note for today's graph. Later I'll show you the graph, okay. And you can actually watch this video again, yeah. And today's video I'm recording, I can actually put it over there. Okay, you can just watch and then try to understand today's lesson, yeah. So this one I will share to you, but now I will summarize again, okay, in terms of here, yeah. Hold on. Wait, guys. Yeah, basically I wanted to erase this, okay, but I didn't erase. It's okay, we'll just straight away we use this. Okay, now if you look at this, this is the summary, yeah, of today's lesson. Yeah, so if you look at this, okay, I will use the blue pen. Yeah, you just follow the blue pen. Now if I have, okay, if I have the strong acid, okay, and strong base. Okay, so if I have, for example, ACl, okay, reacting with sodium hydroxide, ACl pH is 1, sodium hydroxide pH is 13. So you start from 13, you end with 1. Okay, and then the drop, the sharp fall is from 10.5 to 3.5. 10.5 I put over there, 3.5 is over there. So you just draw the graph, okay, from here to here. Okay, and then this is going to be the sharp fall. Now we know the midpoint, okay, is going to be 7. Okay, so that is going to be just now I mentioned about this. I will go through equivalence point and endpoint. Yeah, equivalence point is the amount of titrate added enough to complete the titration. So this V is called the equivalence point. Yeah, enough. Okay, enough for completing the neutralization. So what is endpoint? Endpoint is the amount of volume that we use, okay, for the titration where there is a color change in your indicator. Yeah, so do remember endpoint might not be that accurate. Yeah, it might not be that accurate. The more accurate value is the equivalence point. Normally we can determine that by using pH meter. Yeah, so that's the difference between equivalence point and endpoint. Endpoint is for indicator. Equivalence point is the actual value. Yeah, so they are almost the same. Yeah, they are almost the same. So let's actually look at the indicators. So I have put the 3 main indicators over here. So let's actually check. If you use bromothiamyl blue 6 to 7.6, okay, 6 to 7.6 is this one. Okay, bromothiamyl blue. So bromothiamyl blue is still within the drop, you can use that. Phenolphthalein within here, so you can still use phenolphthalein. Methyl rate 4.2 to 6.3, so still can use. So you can still use all the 3. Okay, but if you go to strong acid and weak base, strong acid you see pH 1, weak base 11, so you start from 11. This is 1. So you go from here to here. Okay, the drop is going to be 7.5 to 3.5 equivalence point. Okay, the midpoint is going to be at 5. Okay, so whether we can use bromothiamyl blue or not, bromothiamyl blue 6 to 7.6. Okay, 6 to 7.6 is from here to here, still can use. Okay, within the sharp fall. Okay, whether we can use phenolphthalein or not. Okay, phenolphthalein cannot use 8.2 to 10. 8.2 to 10 is on top. Okay, cannot be used. Yeah, they are not within the range, so cannot use this. Methyl rate 4.2 to 6.3, so within this range still can use, no problem. Okay, how to draw for weak acid, strong base? Weak acid, ethanoic acid is 4, and then strong base is 13. Okay. So equivalence point, okay, is 9, okay, and then sharp fall 7.5 to 11. So you draw, okay, 7.5, 11, 13, and then 4. Okay, you draw the graph. And then let's look at the suitable indicator. Bromothiamyl blue 6 to 7.6. Okay, 6 to 7.6 is somewhere here only, cannot. Okay, 8.2 to 10. Okay, 8.2 to 10 is within the range, can. 4.2 to 6.3 is within here only. Yeah, cannot. Okay, you must be within the sharp drop, which is going to be 7.5 to 11. And if you look at the last one, which is going to be weak acid, weak base. Okay, this is 4, this is 11, so I draw 11 to 4. Okay, and then this is going to be equivalence point, which is 7. So when I try, okay, of course there is no sharp fall, no suitable indicator. Okay, so we will not use any indicator for this. Yeah, so this note, okay, I have given you in the PowerPoint slide. Okay, later I will just send the PowerPoint slide to you guys. Yeah.